Applications of the normal distribution. Normal distribution, example 1. According to census.gov, the average square footage of a house in the United States in the year 2015 was 2,687 square feet. Assume that the square footage of U.S. homes is a normally distributed variable with a standard deviation of 626 square feet. If a house in the U.S. is selected at random, what is the probability that the square footage is less than 3,651? The probability notation of this would be expressed as the probability that the random variable x is less than 3,651. In order to calculate this probability, we will first need to calculate the z-score associated with this value of the random variable. So we will find a difference between the value of the random variable 3,651 and the mean 2,687, and then divide that by the standard deviation 626. This gives us a score of 1.54. So finding the probability that the random variable x would take on a value less than 3,651 is the same as finding the probability that z would be less than 1.54 in a standard normal distribution. The z-score, 1.54, would be a little more than halfway between z equals 1 and z equals 2. We are to find the probability that z would be less than 1.54, which corresponds to the area under the curve to the left of z equals 1.54. Looking at the left column of the cumulative normal distribution table, we travel down until we find a z-score of 1.5. Then we travel to the right until we find a row that crosses up with the column that is headed 0.04. Here we have a value of 9382. We see at the bottom of this table the picture of the normal distribution. The 4 decimal place values in the body of the table correspond to the shaded region in the picture of the normal distribution. The shaded area under the curve corresponds to the probability that z would be less than 1.54. So the probability that the square footage of a randomly selected home in the United States would be less than 3,651 is equal to a high probability of 0.9382. This can be stated another way. Assuming that the square footage of U.S. homes is a normally distributed variable with a mean of 2,687 square feet, standard deviation 626 square feet, then 93.82% of the homes in the United States are smaller than 3,651 square feet. Normal distribution, example 2. The Bureau of Labor Statistics reported in 2016 that the mean hourly wage for registered nurses in the U.S. was $34.70. Assume that nursing salaries are normally distributed with a standard deviation of $11.58. If a registered nurse is selected at random, what is the probability that he or she has an hourly wage that exceeds $54.62? In probability notation, we would state this as the probability that the value of a random variable x is greater than 54.62. In order to find this probability, we would first need to calculate a z-score. So we would need to find the difference between the value of the random variable x, 54.62, and the mean, 34.70, then divide that by 11.58, the standard deviation. This would result in a z-score of 1.72. So finding the probability that the random variable x would exceed 54.62 would be the same as finding the probability that a z-score on the standard normal distribution would be greater than 1.72. The z-score 1.72 would lie between the scores of 1 and 2 on our normal probability distribution, a little closer to 2. We are looking for the probability that z would exceed this value, which would correspond to the area under the curve in this tail. Looking at the left column of the cumulative distribution table, we will travel down until we find a z-score of 1.7. Then travel to the right, where we'd find a row that crosses up with the column which is headed by 0.02. Here we find a value of 0.9573. We see at the bottom of this table the picture of the normal distribution. The 4 decimal place values of the body of the table correspond to the shaded region in the picture of the normal distribution. So the cumulative normal distribution probability associated with the z-score of 1.72 would be 0.9573. But we were asked to find the probability that z would exceed that value, which would then be the area under the curve on the other side of z equals 1.72. So in order to find that, we would need to subtract that value, 0.9573, from 1. So the probability that z would exceed 1.72 would be equal to 0.0427. Another way to state that result is that assuming that nursing salaries are normally distributed with a mean of $34.70 and a standard deviation of $11.58, 4.27% would earn more than $54.62 per hour. Normal distribution, example 3. According to phys.org, the average fuel economy of vehicles in the US in 2015 was 24.8 miles per gallon. Assume that vehicle fuel economy in the US is normally distributed with a standard deviation of 4.6 miles per gallon. Find the probability that a randomly selected vehicle in the US would be rated for the fuel economy that is between 15 and 33 miles per gallon. In probability notation, this would be the probability that 15 is less than x is less than 33, or in other words, the probability that x is between 15 and 33. In order to find this probability, we will first have to find both z-scores for these values of the random variable. We will do this by finding the difference between the value of the random variable 15 and the mean 24.8, then divided by 4.6, the standard deviation. Here we get negative 2.13 as our z-score. We will need to do this again for the value of the random variable 33. This calculation would give us a z-score of 1.78. So finding the probability that x would be between 15 and 33 is the same as finding the probability as our z-scores being between negative 2.13 and 1.78. A z-score of negative 2.13 would be located just to the left of a z-score of negative 2, and a z-score of 1.78 will be located between the scores of 1 and 2, but a little closer to 2. We are to find the probability that a randomly selected value of the random variable is between those two values. So in other words, we are looking for this area in green under the standard normal distribution. Looking at the left column of the cumulative normal distribution table, we travel down and we find a z-score of negative 2.1. And then we travel to the right until we find a row that corresponds with a column headed by 0.03. Here we find a value of 0.0166, and we see at the bottom of this table the picture of the normal distribution. The 4 decimal place values in the body of the table correspond to the shaded region in the picture of the normal distribution. Now we will find the area to the left of the positive z-score that we calculated. Again, looking at the left column of the cumulative normal distribution table, we travel down until we find a z-score of 1.7, and then travel to the right until we find a row that crosses up with the column headed by 0.08. Here we find a value of 0.9625. Again, at the bottom of this table, we see a picture of the normal distribution, and the 4 decimal place values in the body of the table correspond to the shaded region in the picture of the normal distribution. So in order to find the area shaded, we will need to find the difference between 0.9625 and 0.0166. This gives us a probability of 0.9459 that x would be between 15 and 33. So the probability that a randomly selected vehicle in the US would be rated for fuel economy that is between 15 and 33 miles per gallon would be 0.9459. This can be also stated as assuming the average fuel economy of vehicles in the US for 2015 is normally distributed with a mean of 24.8 miles per gallon and a standard deviation of 4.6 miles per gallon. 94.59% would be rated for fuel economies between 15 and 33 miles per gallon. Let's take out our student notes and follow along. The standard normal distribution curve can be used to solve many practical problems. Assume the variables presented here are all normally or approximately normally distributed. First, we transform the original variable to a standard normal distribution variable using the following formula. That is, z equals to x minus mu divided by sigma. In other words, we take z equals to the value minus the mean divided by the standard deviation. Now, we also want to note that typically you will round to the nearest 2 decimal places. In order to find the area under any normal curve, let's follow the following steps. First, we will draw a normal curve and shade the desired area. Step 2, we will convert the value of x to z using the formula z equals to the value minus the mean divided by the standard deviation. And step 3, find the corresponding area using the table or your calculator. Let's do an example. An adult has on average 5.2 liters of blood. Assume the variable is normally distributed and has a standard deviation of 0.3. Find the percentage of people who have more than 5.4 liters of blood in their system. Again, step 1 will be to draw a normal curve and then shade the desired area. Here is a normal curve, and notice that the mean is in the middle of 5.2. And we want to find the percentage of people who have more than 5.4 liters of blood in their system. Notice that I am shading to the right of 5.4. Please sketch this on your own paper. Step 2, we're going to use the formula to find the z value, which will correspond to the table. So here, 5.4 is the value that they indicate in the problem, minus the mean of 5.2 divided by the standard deviation of 0.3. This reduces down to 0.67 rounded to 2 decimal places. Now use the table or your calculator to determine the area to the right of z equals 0.67. Now keep in mind that the area under the standard normal curve to the left of the z-score, and then use that area to find the area to the right. Keep in mind that this question is asking for more than. So in this case, we're going to go ahead and subtract the value we find from 1. So once again, this 0.7486 is the area to the left of our z value of 0.67. We are subtracting it from 1 to find the area that is to the right of that value. Therefore, 25.14% of adults have greater than 5.4 liters of blood in their system. Next example. The average monthly mortgage payment, including principal and interest, is $982 in the United States. If the standard deviation is approximately $180 and the mortgage payments are approximately normally distributed, find the probability that a randomly selected monthly payment is A, more than $1,000, B, more than $1,475, and C, between $800 and $1,150. Let's go ahead and start with part A, and the first step will be to sketch a normal distribution curve for monthly payments of more than $1,000. Here, notice I am shading to the right of 1,000, 1,000 being right here. Next is to find the z-score. We'll use the formula once again, where we take the value in question, subtract the mean, divide by the standard deviation. Here we get 0.10. And now we go ahead and take a look at the table, and to the left of our z-score of 0.10, you find the area of 0.5398. But as the previous picture indicated, the normal curve that is, we're looking for the area to the right of 0.10. Therefore, in this particular case, we are going to subtract from 1 0.5398 to get our actual answer of 0.4602. B. Let's look at the normal distribution for the monthly payments of more than $1,475. Here's our sketch. Notice here we have a very tiny area to the right of the value 1,475. Now we find the z-score. Once again, it's the value minus the mean divided by the standard deviation. In this case, we get 2.74. As you can imagine, the area to the left of this z-score of 2.74 is quite large. In fact, you'll notice it's almost 1, 0.9969. But once again, since we are looking for the area to the right of that z-score, we subtract this value from 1. In other words, 1 minus 0.9969 is 0.0031. Finally, let's go ahead and take a look at the normal distribution curve for monthly payments between $800 and $1,150. Here is a sketch. Now, in this case, we're going to look for two z-scores. The first being for the monthly payment of $800. Once again, it's the value minus the mean divided by the standard deviation. In this case, we get negative 1.01. Doing the same thing to find the other z-score gives us 0.93. And as we have done before, here we are looking for the area between our two z-scores. So subtract the smaller area from the bigger area as follows. 0.8238 minus 0.1562, giving us an area of 0.6676. I invite you here to pause the video and verify that these two areas come from these two z-scores, subtract them, and verify that you get the same answer as I do. Now, let's find specific data values for given percentages. Using this formula, z equals the value minus the mean divided by the standard deviation, let's go ahead and solve for x, then use this new equation to find specific data values for given percentages. So in solving for x from the formula here, we start by multiplying both sides by sigma. That will give us the z-score times sigma equals x minus mu. Now, as you can imagine, we add mu on both sides. Mu's cancel. And I'm left with our specific data value equals to the z-score times our standard deviation plus mu. The formula for finding the value of a normal variable x is as follows. Now here are the steps for finding data values for specific probabilities. Step 1. Draw a normal curve and shade the desired area that represents the probability, proportion, or percentile. Step 2. Find the z-value corresponding to the desired area from the table or calculator. Step 3. Calculate the x value using the following formula. X equals the z-score times your standard deviation plus the mean. Here's an example. To qualify for a police academy, candidates must score in the top 10% on a general abilities test. Assume the test scores are normally distributed and the test has a mean of 200 and a standard deviation of 20. Find the lowest possible score to qualify. First, draw a normal distribution curve and shade the right-hand 10% of the area. As you can see in this picture, a normal distribution graph, I have shaded the right-hand side, or at least the 10% of the right-hand side. Notice here, the mean in the middle is 200. Step 2, the area to the left of 0.1, shaded on the right, is 1 minus 0.1, which is 0.9. To make it more clear, the area to the left of the initial shade is 0.9. So now we find the value from the table or a calculator corresponding to 0.9 area to the left. As you can see, the answer is z equals 1.28. Step 3, we now use this value in the formula x equals the value times the standard deviation plus mu to find our actual value of x. Here we get 225.6. So in conclusion, a score of 225.6 should be used for the cutoff. Anyone scoring 225.6 or higher qualifies for the academy. In order to qualify for a medical study, an applicant must have a systolic blood pressure in the 50% of the middle range. If the systolic blood pressure is normally distributed with a mean of 120 and a standard deviation of 4, find the upper and lower limits of blood pressure a person must have in order to qualify for the study. Once again, our first step will be to draw. Mark the middle 50%. This will leave 25% to the left of the middle and 25% to the right of the middle. Let's go ahead and use the table or technology to find the z-values that correspond with the area of 0.25 to the left and 0.75 to the left. Those values would be negative 0.67 and positive 0.67. This makes sense because the previous picture was symmetrical. Once again, I invite you to pause the video and verify. It's always best to look up these numbers yourself on the table and not to completely depend on me. Step 3. Use the formula to calculate the two values of x, using each of the z-values, 120 as the mean and 4 as the standard deviation. The first will be negative 0.67 times 4 plus 120, which gives us 117.32. The other, 0.67 times 4 plus 120, 122.68. Conclusion, in order to qualify for the study, an applicant must have a systolic blood pressure between 117.32 and 122.68. Determine normality. There are a variety of ways to determine if a distribution of values is normally or approximately normally distributed. The easiest way to check for normality is to draw a histogram for the data and check its shape. Another way is to use the Pearson coefficient, PC, of skewness, or the Pearson's index of skewness. That would be using this following formula. That is 3 times the quantity x bar minus the median, all divided by s. If the index is greater than or equal to +1 or less than or equal to -1, it can be concluded that the data are significantly skewed, in other words, not normal. Also, we should check the data for outliers by finding the outlier boundaries as defined by the following. The lower outlier boundary is going to be Q1 minus 1.5 times IQR. IQR stands for the interquartile range, as we've learned before. The upper outlier boundary is Q3 plus 1.5 times the interquartile range. And let's recall that the interquartile range is Q3 minus Q1. Keep in mind that Q1 is the median of the first half of data, and Q3 is the median of the second half of data. Let's do an example. A survey of 18 high-tech firms showed the number of days inventory they had on hand. Determine if the data are approximately normally distributed. First, we will construct a frequency distribution. You'll notice here that we have classes 5 to 29, 30 to 54, 55 to 79, and so on. And the frequencies of each class is shown here. There are 2 high-tech firms that are in the 5 to 29 range, 3 tech firms that are in the 30 to 54 range, and so on. Once you have your frequency distribution established, next will be to draw a histogram. We have drawn histograms in the past, so this should not be too difficult for us to do. This graph is looking normal, but it's always good to make sure. The shape basically looks like a normal bell curve. But once again, we must verify this. The next will be to use the formula for the Pearson coefficient of skewness. Determine if there is an indication that the distribution is significantly skewed. So here, as you can see, we use the x bar minus the mean, all divided by s, the standard deviation. Notice here we get 0.148. Since this value is so close to 0, this does not indicate significant skewness. Thus, data may be approximately normal. And last but not least, we go ahead and check the outliers to know for sure. Using the formulas, again, we have done this before. Use the median of the first half minus 1.5 times the interquartile range, which will here will be 45 minus 1.5 times 53. We get negative 34.5. The upper outlier boundary will be the median of the second half of data plus 1.5 times the interquartile range. In that case, it will be 98 plus 1.5 times 53, giving us 177.5. Our interquartile range, again, is 53. Here, there are no outliers, because as you recall, outliers must reside outside of these boundaries, negative 34.5 and positive 177.5. Refer back to the table at the beginning of this example and you'll see that no data value lies outside of these boundaries. Again, there are no outliers. And because of these last three indicators, it is determined that this is approximately normal. Let's do another example. The data represent the number of runs made each year during Bill Mazeroski's career. Check for normalcy. First, construct a frequency distribution. As you can see, we have our classes and our frequencies of those classes. Now that we have our frequency distribution, construct the histogram. We'll notice here that this is not looking normal. But of course, in order to verify this, let's go ahead and take a look at the Pearson coefficient of skewness. Here we take 3 times x bar minus the median divided by the sampled standard deviation. In this case, we get negative 0.986. Now this is not less than negative 1. However, because it is close to negative 1, the coefficient indicates that there could be significant skewness. Let's go ahead now and check the outliers as well. Lower outlier boundary, in this case, will be negative 17. The upper outlier boundary, in this case, will be 107. We have the interquartile range of 31. And if we take a look back at the data, there is no data value that's less than negative 17 or greater than 107. So here we have no outliers. Now, despite having no outliers, we still have a situation that does not appear to be normally distributed.